You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Darryl Seligman. Darryl Seligman is a National Science Foundation Astronomy and Astrophysics postdoctoral fellow and a Simony NSF scholar at Michigan State University. His research spans a wide variety of planetary science and astrophysics topics, including small bodies in the solar system, planetary dynamics, and the origins of interstellar objects. He currently serves as the Early Career Secretary for NASA's Small Bodies Assessment Group, which helps shape NASA's exploration and research priorities for asteroids, comets, and other minor planets. He's also a member of the Rubin Observatory Users Committee. Starting in August 2025, he will begin his next chapter as an assistant professor at Michigan State.
Darryl Seligman, welcome back to the program.
Thank you for having me, John.
Darryl, Chemical Mysteries with 3I Atlas. It is a weird one, and it turned green since we last spoke. And the chemistry seems unclear, even though comets turning green is actually fairly normal. But this one seems to be doing it a different way. Do you know anything about that?
Yeah, I think the turning green thing, like you said, that is something that's typically seen in comets every now and then. So that was, I think, a little less surprising than people made it out to be. But I think the one there's been several, I know that you're kind of alluding to this, but there have been several different compositional things that were maybe surprising. The most remarkable, I think, were those JWST observations, so that CO2 detection.
Got a lot of it, but I always try to keep in mind that this is from another star system under conditions that we don't know what the conditions were that this thing formed in. So maybe there was more available CO2 in that star system or something like that. But what throws me for a loop, honestly, is the nickel to iron ratio stuff. Where is the iron? But I think we're going to find the iron, and it might have been masked. What are your thoughts on that?
Yeah, so the nickel to iron ratio stuff that is somewhat mysterious. I mean, if we just take a step back for a minute, you might remember that back in either 2020 or 2021, it took a while. It might have been 2021 that it was published, but there was a paper published in Nature where they actually detected something very similar in 2I Borisov. So it is not actually unprecedented to see that. I'm just going to look it up real quick. I think it was 2021. Yeah, it was 2021. I'll send you the link to the paper, but it was atomic nickel in the coma of interstellar comet 2I Borisov. So I think this kind of puzzled everybody. And I'd say that there hasn't been, I don't know, maybe there hasn't been that much attention to that paper even back a couple of years ago. But I think it was primarily because people didn't really know what to make of it. And then the fact that 3I Atlas, we're now seeing atomic nickel, or, there is the nickel to iron ratio is weird, but we're seeing that again. That seems to be a common theme, actually, in interstellar comets.
Yeah, and I'll go out on a limb and start wondering about the nature of the supernova that populated that. Is there something we don't quite know about nickel versus iron production in supernovae, or can iron be depleted somehow in the interstellar medium? Because this thing's been floating around out there for billions of years, apparently, in the ISM. What's that do to an object? There's all sorts of questions. What is the latest now, as of today, with 3I Atlas? What do you know, perhaps, about the Mars observations?
Right. So the Mars observations, those are, I'm glad that we're get there. And I do want to circle back to the weird composition, because that is, there are lots of interesting, I think one thing that maybe has gotten lost and it's worth focusing on is what possible natural interpretations there are for the iron to nickel and the CO2. The Mars observations right now, that's pretty exciting. The unfortunate thing is that this government shutdown happened just within a couple weeks of 3I Atlas's closest approach to Mars.
It's outright maddening.
I don't know. Ross was texting me about it. Yeah, exactly. Maddening, right? I want to caveat this with saying that I am not part of any of those Mars spacecraft missions. So I want to be really careful to not speak for any of the missions or speak as if I'm one of the people making decisions for any of those missions, because that's kind of all of that is like well above my pay grade. So I don't want to speak for any of the specific Mars missions. But, we have this really exciting opportunity to look at 3i Atlas up close. We don't get to see it. We can't look at it from the Earth right now. And it's very maddening, as you said, because when a comet gets closest to the sun, so at perihelion is when that's when most of the fireworks go off. So that's when you really want to see, because that's when you have the best chance of seeing not only the most activity, that's when you get the reason it's so important to look when it's close to the sun is that's when you get the most holistic or realistic view of what the nucleus is. Because when you look at stuff really far out, a lot of the volatile species that you'd expect to be there could very easily be there, but it's not warm enough for them to be active. A measurement of a hypervolatile, for example, like CO, really, really far away, that is very interesting. When the comet is really far away, that's interesting, but it also isn't necessarily telling you about that's not an unbiased view of the composition of the nucleus, because water isn't even supposed to be active. It's not, you're even not even warm enough for water to be active when you're past 4 AU, say. So it's really, right now is when you really want to get information on 3i Atlas. We already knew that we weren't going to be able to observe 3i Atlas from Earth around now, back when we discovered it, because we could map out where it was going to be. So as maddening as that is with the apparition, we had months to kind of get over that, right? So we were upset about that, but we kind of figured out we weren't going to be able to look at it from Earth during this really important time going on right now. But I think a lot of us were banking on the Mars spacecraft being able to observe it. And the good news, I think you'll be happy to hear, is that as far as I know, with the caveat that I don't want to speak for any of the missions, as far as I know, every single space mission which was planning on observing 3i Atlas during this time, which is basically every single one which could have, they're still moving forward with those observations. So all of those observations are still happening. It's just that because of the government shutdown, they're not able to like publicly release any of the observations or any of the data. So they can't even, for example, if you are, it's kind of, there's pros and cons of working at NASA, but if you are, I am not officially a government employee right now as a Michigan State professor, but there are a lot of scientists, especially a lot of ones that work on missions or parts of missions, they work at NASA or at Goddard or JPL or something like that. If you're in one of those camps, then just to submit a paper, you might hear my cats freaking out in the background.
Makes for interesting listening.
Yeah, we just got a kitten, and my kitten annoys his older brothers all the time. So that's what that was. Sorry if you could hear that. Where was I? Right. Yeah. So so there are lots of great things about working at NASA, but one thing is that any paper if you're going to be a co-author of a paper, you have to get that paper totally cleared and okayed by different offices, depending on exactly what part of NASA you work at. So I think right now with the government shutdown, they don't even have the ability to get there, even if they had all of the observations that they took with the Mars missions analyzed and ready to go, ready for public release. They don't even have the ability to submit the findings to a journal, which is certainly I'm imagining, I don't want to speak for any of the scientists who are on those missions, but kind of like empathetic to them right now, because I imagine that it's very, very frustrating.
It is fun to imagine, though, because one of the observations will be done by the venerable Mars Reconnaissance Orbiter, which is one of my favorite spacecraft ever. And it is old now, but still unbelievably capable.
Right.
And that should, my sense is, allow us to sort of constrain the actual size of the object and finally lay that to rest. Do you think that that's the case, or do you think that the Hubble Space Telescope observations basically nailed it as far as size, nucleus size?
Yeah. Okay. So I think those Hubble Space Telescope's observations were very enlightening. It was somewhat surprising that we didn't get a better size constraint from the HST observations. But remember, because basically the way that Dave Jewett sets up those HST observations of a comet, it's like basically very fine-tuned to nail the size. So one of the most important things to measure for a comet is the size of the nucleus. And as you know, it's very difficult to measure the size of a nucleus of a comet when all you're seeing is coma, right? It's much easier to get the size of an asteroid. So Dave is very good at setting up the observations with HST such that they're able to get a nucleus size. It's very tricky to do it, but the way you do it is basically you get a sufficiently sensitive image such that you can take the coma and actually remove the coma from the image and see a little bit of excess light in the center from the nucleus. And that's how you then constrain, say, like an upper limit on the size or even a detection of what the limit is. So for example, when Borisov came through, Dave was able to do that with HST and was able to actually measure the size of the nucleus with some uncertainty, of course, but very good measurement. And then with 3i Atlas, the issue was something went wrong with HST. So I think it was some gyroscope issue. I'm not sure exactly what happened, but they ended up executing significantly less time than the observations were supposed to. So I think I'll have to go and double check the numbers, but I think it was like they only ended up with something like 10 minutes worth of HST observations. So we should be kind of thankful that it worked as well as it did, honestly, based on the difficulty with the situation that was going on. The HST observations provided they didn't detect, so in those observations, they did not detect the nucleus. So that basically gives you an upper limit on how big it could have been. And I think that exact upper limit that Dave calculated was something like 2.3 kilometers. I think it's that. Don't quote. Well, I guess you have to quote me on that, but I can look it up if you want. But it was that, but it's very possible that it's significantly less than that as well, because they didn't actually detect it. So more information about the nucleus would be very welcome at this point, because the size of the nucleus tells you so much about things like the formation of the object, possible formation mechanisms for the object, and subsequent evolution. Like how, if it was, for example, if it lived in an environment like the asteroid belt today, you'd expect that things that are pretty big typically will end up having a lot of impacts. And then you get some of those collisions can actually fragment, and you'd actually expect there to be a lot more smaller objects, for example. So it is really important to get the nucleus size. I don't want to say too much about, while I agree with you, John, about how exciting it is with some of these Mars missions, the possibly getting the nucleus size, I don't want to speculate too much on the success that they're going to have with doing that, because a lot of that are kind of, obviously we're going to have to wait for some of the results, which is frustrating, but it seems like, I think optimistically we can hope for that, but realistically we also have to kind of remember that all of these space missions, which are hoping to observe or planning on or currently observing 3i Atlas, none of them were meant to observe to take observations of an interstellar comet. So a lot of those, I mean, for some of the things at Mars right now, I mean, some of those cameras are like 20 plus years old. So it's amazing that it's amazing how good of a condition they're in and that they're still working, but they certainly weren't designed for this. So I think it's going to actually, I think we should have some, I don't know if respect is the right word, but have some respect for the teams of people who have to analyze this data, because it's not as simple as it sounds, right? Because they're trying to get observations of a comet that is still like, while it's close to Mars in like solar system context, in terms of the actual instruments that exist on things like the rovers, the comet is way further away than things that they're meant to be observing or taking any measurements of. So we should be grateful for any information that we get, but with the understanding that these mission teams are working very hard to try to interpret and analyze and interpret observations of this interstellar comet that these instruments were not designed to take, right?
Yeah, but it's still amazing because they thought of something that they could do, and we'll get what we get from it. But it's still pretty amazing because MRO also was not designed to take a picture of another Mars craft parachuting down and landing.
That's right.
So
That's a good point.
I have a lot of respect for those people, and I'll bet they'll tease stuff out of it that we may not have expected. Now, any word from ESA and their probes?
So right now, there is close to nothing being circulated, right? Like, as you know, I think we're in a very similar kind of situation where maybe it's not quite like a government shutdown that's affecting things, but a lot of times when NASA or US assets go down, that also affects other countries significantly, because a lot of times the US have some participation. Like a lot of these ESA missions have things like international what do they call them? They're like international science programs. So you can have like basically a whole subset of the team are American or some other countries. But so NASA will be heavily involved with some of these other countries' missions, even if that's not the primary funder. So the government shutdown really bleeds over into the whole space asset global space asset ecosystem, if that makes sense. So I think it's really, really detrimental. But right now, I think we can be excited about like you said, we could be very excited about the results that have to be coming in the next couple of weeks, but there's nothing super exciting to share just yet.
Yeah, but I'm content with the idea that the observations are still being made.
Right.
Data is being taken. It's just the interpretation and getting it out there and all that's held up. But the spacecraft did observe, so we will get something.
Absolutely.
No matter what. And I do also, even though none of these spacecraft were designed for this, we also have an array of them. I believe there's 4 spacecraft looking at it, and they all have different instrumentation. So that'll be interesting. But back to the chemistry. Let me ask you my usual off-the-wall question. When a solar system comet comes cooking through and it comes to a perihelion much closer to the sun, say it evaporates, does that actually tell you more about the comet if the whole thing just sort of disintegrates going that close to the sun? Just in general about comets.
Wait, so let me make sure I answer the right question. Are you saying in general, just any comet, not just typically
any comet, anything that any dirty snowball that comes in, is it better observationally for it to get as close to the sun as possible to characterize its chemistry?
I see what you're saying. That's a good question. So I think generically the answer is yes, with some caveats. So I think for most cases, yes. And the reason is that basically what I was trying to get at before about getting the most holistic view of the comet nucleus. So let's take a step back. When a comet gets close to the sun, right? It starts the surface, you're getting more irradiation from the sun. That means more solar photons hitting it, it's heating up, and more ice is turning into gas and sublimating. What ends up happening is that the closer you are to the sun, the warmer it'll be, and you'll have different types of ices starting to sublimate. So, for example, when you're really far away from the sun, when you're out past like 4 astronomical units, like 4 times the Earth-Sun distance, you're not even able to see water, really. Like water isn't really expected to be vigorously sublimating because it's not warm enough for that. So the closer you are to the sun, the warmer you are, and then the more kind of, it's kind of like once you get warm enough for a certain ice to sublimate, you're always above that temperature. So that ice always, if it's there, if it's still in the nucleus of the comet, it should still be going. So you can't get too warm. But you can't, if you are too cold for a certain ice to be active, then it'll just shut off. Fundamentally, the most informative thing you can learn about a comet is what different ices there are, but most importantly, what the ratios of those ices to each other are. So for example, how much water there is compared to CO2. So just the CO2 detection is while the JWST CO2 detection is it's like a great scientific achievement. It's an amazing discovery. What's really powerful is the CO2 to water ratio. So how much CO2 there is compared to water. So in that regard, the closer that you get to the sun, absolutely the better it is for interpreting what the composition of any comet is, because that is real. Those ratios are kind of what tell you the fundamental things about that comet. In some sense, those ratios are more fundamental to the nucleus of the comet than any single species detection by itself. And those ratios, because they are fundamental to the comet, they also tell you things like where the comet could have formed. So, for example, if you measure, this is just an example, but if you measure that a comet has a really high amount of water compared to how much CO2 it has, when you're warm enough for all of those species to be active, then you know that, if there was more CO2 there, it would be actively sublimating the way that the water is. That's telling you really fundamentally that nucleus of the comet has more water in it than CO2. And then that tells you that it probably formed in the kind of closer regions in the solar system, for example, because if you form at a closer region, potentially you could form where water freezes out, but CO2 is not frozen out. Does that make sense?
Yes, it does. It just occurred to me, it's really interesting time for comets because it's not just the, 3I Atlas coming through. There's also 2 solar system comets.
Right. That's
that
right.
are binocular. They're binocular level detectable at this point, all at the same time.
Yeah, it's amazing. Have you been able to see any of those?
Not yet. I think it's going to take me a few more days to spot them at dusk, or spot 1 or 2 of them, whatever I can do at dusk. But I am going to try with 10 by 50 binoculars. And if I can get an actual position, I'll get a telescope out. But I am going to try to pick them up with big binoculars because, but the thing is, Darryl, it's ruined for me because I saw visually and photographically and everything else Hale-Bopp.
Oh, right.
And nothing has ever gotten quite that good. So I'm like,
Yeah.
nah.
Some old naked eye comet just doesn't do anything for you anymore.
Yeah, not anymore. I've been ruined since the 90s because of Comet Hale-Bopp. Now, my next question is this. All right. The sun spike that 3I Atlas is showing, which to me suggested that it was a matter of preferential heating somehow. What do you think the mechanism, what they call an anti-tail, but it's not actually an anti-tail. That's a different phenomenon. That's a perspective phenomenon with comets. But this is actually something the comet is doing. What do you think that is? Do you think it's just preferential directional stuff regarding the sun and composition of the object?
So there's a couple of different possibilities, right? And then just to be clear, you're talking about the sunward direct, like back a couple months ago, even we had hints of it, but the fact that the morphology of the tail seems to be pointed in the direction of the sun.
Yes, one way or another, it seems to be. Yeah. That's what I'm referring to. Yeah.
Yeah.
That may have changed, by the way. I mean, it may have gone away by now, but it was an interesting feature. Sort of unusual.
Yeah, I think we reported that. Yeah, I was on some papers that reported that, but there are basically all of the observations that were taken from the get-go, from when it was discovered up until a couple of weeks ago when we stopped being able to observe it from the ground. All of them agreed that the morphology of the tail looked like that, it was pointing in that specific direction. So that, first of all, it's not unprecedented, right? So you see stuff like that in solar system comets. It's not the most typical thing. In general, the morphology of the tail can tell you the morphology of the tail can tell you different things about both the physical processes and the physical properties of the things that are driving the sublimation. So one classic thing that you'll kind of hear, well, I don't know if everybody hears this classically because I don't know how much people typically learn about comets. I think it's not that much, but because I'm a little jaded right now because I'm teaching introductory astronomy at Michigan State for the first time. So I'm like, oh, right, everybody learns like the very, very basics, but that's totally not true because most people don't take intro astronomy. But one of the classic things you'll kind of hear is, okay, a comet will have a tail that's in the direction pointing away from the sun, right? The reason for that is that once the material blows off the surface, remember there's ice that heats up and sublimates, producing an outflow, but then there's also kind of little dust particles. So dust is our blanket term for things going from millimeter-sized rocks to centimeter-sized pebbles all the way down to micron-sized dust particles. So we've got all of these different kind of like sandy rock boulderish material that's getting blown off as well. What happens is that eventually radiation pressure from the sun, so the solar photons then hitting the tail, will push on some of the dust grains in that tail and push them all away from the sun. And so basically one way to what's actually going on is a lot of times when you see those like magnificent tails pointing away from the sun, a lot of times that material actually blew out first in the direction of the sun and then was pushed away. Because the most natural thing if you think about what's going on the surface of the comet, the most natural place for the ice to be outgassing from in the first place is in the direction of the sun. Because that's kind of, if you think of the comet, if you think of the surface of the comet, the part that's pointed at the sun, I wish I had a diagram right now, but like the part that's illuminated by the solar, if you look at the nucleus of a comet, if you put the sun down and let the solar photons kind of illuminate one of the hemispheres, then you'll see that half of the surface at any given time is illuminated by the sun. That is also the part of the surface that is most vigorously heated at any point in time. So that part that's illuminated, that's where you'd imagine the ice kind of, at the very zeroth order, ice will sublimate and come off the surface, and it'll actually be blown in the direction of the sun. Then after that happens, solar radiation pressure, so that means solar photons come and then they kind of hit the dust particles that are in that cometary tail and push it away from the sun. And that will then drag some of the gas along with it. So a lot of times when you classically see the cometary tails pointing away from the sun, that's actually because radiation pressure has acted on them after the fact. So like after they've been blown off the comet. For 3i Atlas, it's unclear exactly what's going on. I think we need a good amount. We basically haven't had time to do really we haven't had time to do detailed numerical or computer simulations to try to figure out exactly what could produce the tail morphology that we're seeing, because it kind of, it depends on things like, how far away from the sun were you? How far away from the sun were you? How much heating you got? And what different type of ices were there, and what different types of dust grains you allowed to be in the coma. But I would say for now, like right now, it seems like the fact that that sunward feature of the tail, that's probably telling you something actually about the physical properties of the dust grains that were blown off. Like the dust grains, it's possible that those dust grains were on the larger size. Like we know that happened in 2I Borisov, that the dust grains typically were quite a lot bigger than those that you see in solar system comets. The interpretation of that is kind of still up in the air. But if something like that happens, then they won't be as affected by radiation pressure. And so it's much easier to see a sunward tail if you have those larger dust grains. Does that make sense?
It does. And you can sort of visualize this process by thinking about snow in the sun. And if it's in the sun, it goes away faster than snow in the shade does.
Right.
Because it's in direct sunlight, so it's being heated. And so that you would have it preferentially moving towards the sun to begin with, but the sun is working like a windstorm, and it's pushing it back. So you've got not only light pressure, but solar wind, particles, all kinds of stuff that push it back and create the characteristic long tail of a comet. But one of the interesting things about comets is that they can create, if you go through that tail, it can create a meteor shower. And that means that you can also collect samples of it. Are the particles and dust, especially, because I want some of that dust from 3i Atlas, can we send out a mission to go and do a sample collection after the fact in where it actually passed through, and maybe get a few particles of 3i Atlas? Is it possible to do that kind of a mission and get some dust from this long after the fact? I mean, 2 centuries from now.
Okay, so yeah, so there are several different parts to that question, and I want to make sure I kind of address everything. So first, yeah, I love your analogy of the like sun and the snow on the ground and sun heating it up. Everybody can kind of relate to that. Did I answer your last question like sufficiently? The one
Yeah,
about the
yeah.
sunward tail? Okay.
Sure.
Okay, there I had a couple different thoughts popped in my mind. So the first one, okay, this also I'm a little biased, right? Because like I mean, on July 1st, I was just obsessively working on 3i Atlas, and a bunch of us put together that first paper about the discovery of the object. In those first couple days, I was thinking exactly what you're asking me. Like, how do we get a sample of this object? It's like we were obviously going to have lots of observations, right? I mean, it's very exciting. It's really great. That lots of people worked very hard to obtain observations immediately upon discovery and since. So that's all really wonderful and very important. But I was thinking the first couple of days, like, how are we going to get what? How did you say it, John? It was like, how do we get like a couple pieces from 3i Atlas or a few?
Yeah, just a couple of dust grains is all I want.
That's exactly right. So the first thing, like you mentioned, like meteor showers. So comets in the solar system do produce meteor showers. So you'll have these like comets, especially ones that get close to the Earth. They will produce these big cometary tails, and then the Earth kind of sometimes the tails, blow out in different directions, and then they get very diffuse so that you can barely even see them. But every now and then you'll get meteor showers and you can basically, the radar experts who take those measurements and track different meteor events. There are these meteor stations all over the globe and also in space that track meteors. You can basically look at those observations, and the experts there will say what they call them the radiants, but it's like what direction are the meteorite particles kind of hitting the Earth from? And then can you tie that to any known comet or active asteroid? So in that sense, you can actually there are comets or active asteroids that you get pieces of them on the Earth that you could just go and get if they survive the fall and become meteorites. So that, I was like, okay, I think I was, this is like kind of embarrassing to admit this, but it was like after like July 5th, July 6th, like that was such a blur because I didn't sleep at all for any of those days because I was just like writing that paper. But I was also it might have been me going a little crazy. I was like, oh, let's see if we can get any like meteorites or is it possible that 3i Atlas has deposited any meteorite action or will deposit any meteorite on the Earth? I think the answer is very, very safely no, unfortunately. So I think it's like I asked some meteor people if there's any shot, and they were like, Darryl, like not in a million years, because it gets like so far away. It's so far away that it's like there's no hope of getting some of the material from 3i Atlas on Earth. Actually, in fact, you had a much better chance of having meteorite material from ʻOumuamua hit the Earth because it got so close to the Earth. Even though it didn't have a big obvious tail, if there was any stuff coming off of it, which we presume there was because it had its non-gravitational acceleration, it would have been much easier because it came so much close. Like how close you get to the Earth is definitely the most important thing for if you're going to get any meteorite material. And so, yeah, there's no hope of getting that from 3i Atlas, unfortunately. It's also, retrospectively, it's kind of obvious because it's like, yeah, there are a lot of comets in the solar system, and not every comet produces meteorite material. In fact, we know that it has to be kind of, I don't know, special. It's got to be kind of a special configuration to produce a meteor shower. So already we know that it's like a rare occurrence in the solar system comets. And the interstellar comets are way less common than solar system comets. So it's very, very unlikely that you'd get meteorite material from any given interstellar comet. However, I think where you're also going, is it possible that we send a spacecraft to get any in situ measurements? Is that what you also want me to talk about?
Yes, but let's get crazy with it, Darryl. I'm gonna one up it. I'm gonna ask a question that probably no comet scientist has ever been asked on a YouTube channel before. So, say in an ideal world, and we have a large comet that comes through, a fairly sizable one that's enough to have craters, and we mentioned that earlier. And we have a sample return mission ready to go intercept it. We go and we get it. Now, we accidentally picked up a meteorite sample, a carbonaceous chondrite sample in the Apollo moon rock samples. So is it marginally possible
Sorry,
that we would.
sorry about that. My cat just like sat on my keyboard, and so that's what all that all that was.
That's fascination. The cat is fascinated. I have one of those too, but I actually, my studio is separate from my house, so the cat is safely
Okay.
over there sleeping in the sun, sublimating, the sublimating cat. But anyway, so say we get the sample return mission out there at an interstellar object large enough to have been hit by meteorites from the other star system. Could we end up with a smorgasbord of materials from that star system of origin when it was still there getting hit by meteorites, and be able to differentiate and say, well, look, this is analogous to a chondrite, but it's stuck on an ice ball. This is separate. This is a different sample. Can you get a 2-for-1 from an interstellar object sample return mission?
Yeah, that is a very, yeah, that is a crazy question, but it's super interesting for sure. I have never even considered really that possibility, but presumably, I mean, maybe we can, maybe we can basically use that as part of the rationale for why we convinced NASA to get something together to go smash into an interstellar comet. So it seems like there's no, besides it, I mean, it seems like an unlikely occurrence, but there's no showstopper reason that I can think of off the top of my head as to why that definitely won't work. So, okay, if we take a step back, if we are ever in the situation, John, where you and I can basically talk on air about the results of an interstellar comet mission, I think my life's work will be complete. So I'll be pretty satisfied just because we got something to an interstellar comet and potentially brought it back. So I won't be upset. I don't think I'll be upset if there's not micrometeorite material or carbonaceous chondrite material from the samples that we get back from an interstellar comet. I think if we're able to, it would be a remarkable achievement of both scientific and engineering achievement and humanity if we were able to do a space mission to an interstellar comet from another solar system. So if we're in that position and then people are arguing about the interpretation of the data, I think that's a wonderful situation to be in. It's possible, I guess. I think the hardest thing actually, so while I like where your imagination is going, the hardest thing probably would be figuring out like how to access that type of material, because it's going to be one thing to remember, right? If we're going to just think about 3i Atlas, like it's moving super quick. So we wrote this paper, this undergraduate I've been advising wrote this paper. His name is Atsuhiro. He wrote this paper that was just accepted about sending potentially like outlining what kind of spacecraft could do a rendezvous with 3i Atlas. And we did this back a couple months ago when it was still feasible. So we showed that if we had sent some of those Mars spacecraft basically like before the end of September, we could have actually probably pretty easily gotten to intercept 3i Atlas. That's now probably infeasible. But back then, I mean, that's what we did the paper in the first couple of weeks. So we were thinking maybe we could send something. The thing is that the object's moving really fast. So if you allow for significant wiggle room, given the like fact that you only have a couple of weeks to get there and you don't have like years to do the trajectory planning and all of that, you really need, I think, a large room for error. What that means is that you're way more likely to intercept the tail than to intercept the nucleus for any given interstellar comet, because presumably that tail is kind of, as we've kind of already talked about, it's either getting blown out by radiation pressure or it's getting blown out from the comet to begin with. It's very diffuse and it like occupies a large volume of space, while the nucleus is a really tiny target. So I think it's much more likely ideally we live in a world in 10 years where we're discovering interstellar comets left and right, and we're sending space missions to them left and right. So that would be great. But I'd say that the first space mission we send to an interstellar comet, there's a good shot that we just get the tail, right? And if you just get the tail, you're kind of, what's the word? You're kind of biased. You know what I mean? But like you're kind of biased in the material that you're sampling. So you really are, when you're going through the tail, yeah, you're getting some stuff from the surface, presumably, that came along for the ride, but you're really probing the ice that's sublimating. And that stuff presumably is primordial. So it's like primordial ice that the comet was made from, / that it was built up from when it was forming. So it is totally feasible. I mean, it's really a remarkable idea, John, but it is totally feasible that an interstellar comet that comes through the solar system would have some, meteor type material from impacts with other objects in its host solar system, and some of that stuck to the surface, and you've got kind of crazy, what'd you say, a smorgasbord or something?
A smorgasbord or a sampling. It's its own sample collector, essentially, is what I'm suggesting. And so my whole overarching idea here, Darryl, is get a large sampling of another star system, because it's being delivered to you on your doorstep. You don't have to go there. It already did the space travel for you, but I'm going to up the ante again, Darryl. That's how I operate. A manned mission in the far future to an interstellar comet that is outgassing. Would you go on that mission and try to be the first person to set foot by proxy in another star system, even though that thing is blowing off carbon dioxide and all sorts of stuff? Would you do it?
I think I couldn't say no. I mean, this sounds like something that you'd write a book about, like the science fiction book about, but it's crazy that it's potentially not even, I mean, something like that maybe would happen in our lifetime. I mean, it's entirely science fiction, I guess, at this point, since we are legitimately talking about sending spacecraft to an interstellar comet. I guess, yeah. I think, yeah, I guess I would have a hard time turning that down, even though I have no desire to ever go to space. I think if that were the opportunity to see one of those things up close, and being one of the first people, being the first human to get up close to an interstellar comet, how could you turn it down?
Yeah, and you can play with other ideas. Like, for example, if it's an interstellar asteroid, just an asteroid cooking through, and we're to the stage where we're mining asteroids, somebody might say, I wonder if there's any platinum in that thing, and go out to the interstellar and mine the interstellar material and melt it down. Sorry, were you done? Or did you have something else you were going to say? No, I trailed off into a giggle as is my way.
Yeah. So another thing is that, I'm rotating off, but I'm still basically, we call it the early career logistic coordinator for the NASA Small Bodies Assessment Group. But that's basically NASA runs these AGs. They're called assessment groups, but they're supposed to basically be we hold these couple of meetings every year, and we get all the scientists in the community and write up the findings of everything that we most want from NASA for NASA to do, and NASA then responds to those findings. There is a whole part of this SBAG, you can go look it up if you want, if you're interested. It's all public facing, so there are public facing goals documents that we update. So all of the goals, things that we want NASA to kind of prioritize funding wise. There is a whole subset of SBAG that is devoted to human exploration. And by human exploration, the SBAG is the Small Bodies Assessment Group. So we're talking about comets and asteroids. So specifically, there is a subset, there is significant interest from NASA to do human exploration of small bodies, meaning land a human on an asteroid or a near Earth object or something. And one of the reasons is the asteroid mining thing. But I mean, the main reason is that they see it as a stepping stone to Mars. So it's not the craziest thing ever that you're asking about. We have legitimate scientists. NASA has legitimate interest in sending astronauts to asteroids. So it is not while it is a little out there, it is not showstopper crazy, never going to happen to say go to an interstellar asteroid or comet.
Well, I think that was actually a suggestion that hit pretty high in politics, because I think Barack Obama suggested it. Let's go to an asteroid, and nothing ever came of it. But that was actually something that was mentioned back in the day.
I guess I was I was pretty young when Obama was I was less than high school age. So I was not following politics very well, I guess. So I missed that he said that.
I was unfortunately in my 30s. Anyway, now next question regarding 3I Atlas and its chemistry. So do you suggest or expect, as the chemistry evolves, to start seeing interesting chemical species reactions going on there? Because I'm presuming that's what this nickel is, and that it's a reaction nickel compound forming from other things. And do you expect to see that this thing evolves? And what do you expect to see after it's done passing the sun? Do you expect a different character to this object after it's perihelion and its closest point to the sun and highest sublimation rate?
Yeah, that's a good question. So you're right. I was going to say that earlier about the iron and nickel stuff. So at face value, right, that nickel detection is weird because when they observed the nickel, 3I Atlas was way too far from the sun for nickel to just be vaporizing.
So I wonder about the chemistry. What else is going on?
Right, exactly. So the interpretation is for sure that there is some type of chemical reactions that are happening to form the nickel. There are a couple different avenues, like chemical networks that you can go through to produce that. And it's still kind of up in the air exactly what it is, but you can blanket the way that we're talking about right now. You blanket it with the Comet experts basically say like non-thermal processes, which means it's not hot enough for the nickel to just be vaporizing, but some other things are going on. I mean, there's a lot of really interesting chemistry that goes on in the coma of a comet. So that's certainly what we're seeing, but the exact chemical network to get there is unclear right now.
Yeah, but it's extraordinarily cool because when you're dealing with an object that's much older than the solar system is, that's what I'm worried about. I'm like, well, what was the universe's conditions for star formation and disks, debris disks and everything forming planets back then compared to now?
Yeah.
Was there a difference? Have we had a few more, having had a few more supernovae around us, does that change over time? Does the Milky Way's way of forming solid objects evolve?
No, that's a really, you're exactly right, John. Like that is the money question. And like from exoplanet science, we know that it does. So we know that there is, for example, one of the best known rules or empirical trends of all of exoplanet science is that you're more likely to find a hot Jupiter exoplanet if you have more metallicity. If you're looking at a star with higher metallicity, which means a higher total amount of metals. Presumably, like the obvious interpretation of that is that, oh yeah, well, there were more metals in the disk as well because the star is more metals, so there's more metals in the disk, so you were able to form more planetesimals and comets, asteroids, and then planets. But at the same time, we also know that because, as exactly what you're saying, as the Milky Way gets older, more supernovae go off, and the supernova enrich the interstellar medium with metals. So one possibility is that actually you're enriching as you get older, you're enriching stars with more metals. And so that metallicity dependence, or the fact that you're more likely to see a hot Jupiter around a metal-rich star, maybe it's actually you're just more likely to see a hot Jupiter because more hot Jupiters formed in the more recent Milky Way. This interstellar comet, 3I Atlas, is probably significantly older than anything that we've seen in the solar system before because there are a few caveats that we probably should say, but it was going wicked fast at infinity, which is at least consistent with it being billions of years old, potentially older than the solar system itself. And so it could be, if it really came from one of those planetary systems that formed way before like in the lower metallicity Milky Way galaxy, before a lot of the supernovas had gone off and enriched the galaxy with metals. Maybe it's kind of like one of those, maybe its composition is weird compared to solar system comets because it was formed in a disk that had much less metals. And it was one of those kind of like weird outlier things that formed. Like, I don't know, I'm just spitballing, but you see what I'm saying?
Yeah. And what part of its disk did it form in?
Mm-hmm.
I mean, well, being so carbon dioxide rich, probably formed pretty far from its star, right?
Yeah, well, that's I think at the beginning episode I said I wanted to focus on the JWST observation. So it was JWST and SPHERE-X. Yeah, JWST and SPHERE-X got the CO2. It was Swift that got the OH and the H2O. But yes, so the high CO2 especially the high CO2 to water that was measured, that is kind of remarkable because you can think of it basically like if you just blanket it like H2O, CO2, and CO, those as the three kind of main drivers of activity in comets, you could think of it like basically the existence of those species tells you where in the disk it formed with respect to those respective ice lines. For reference, the H2O snow line in our solar system is around Jupiter. The CO2 snow line is around Saturn, and the CO snow line is around Neptune. So the fact that it had a lot of CO2, but not a lot of CO and not a lot of water, potentially is telling you that actually it had to form in this like sweet spot. Like, yes, far out, but not too far out. Because if it formed too far out, I mean, carbon actually would rather be a CO than a CO2. So I think it's actually the reason those CO2 observations are so amazing to me is that it's telling you that I think that 3I Atlas had to come from a relatively narrow region in its protoplanetary disk. So that actually kind of like, even though with an interstellar comet, you can't trace it back to a host system, that tells you a remarkably specific amount of detail about the ambient environment in which 3I Atlas formed.
Do you think that goes so far as to be able to determine the type of star that it formed near? Meaning, obviously, it's overwhelmingly likely to have been a red dwarf, but do you think that the profile might change if it formed in a system of an F-type star, something like that, and we could maybe tease that detail out of an interstellar object like this?
Yeah, I mean, that's actually like exactly what my one graduate student is working on right now. So the short answer is yes, I think potentially. You can't trace any interstellar comet back to any given star because the galaxy's orbits are chaotic. But you can kind of roughly say the speed at which they're entering the solar system kind of roughly correlates with what type of star it comes from, because older stars in the galaxy move faster on average. So then there's the fact that the chemistry traces it to a location in the disk. So I think that by combining, basically what you have to do is you combine the information, you get all these different pieces of information. If you put them together, there's basically the chemistry you're seeing on the comet. That's kind of giving you a narrow region in a disk. It has to be. And that narrow region of a disk, like those locations of the disk that has CO2 frozen out, but not CO and not water, that changes as a function of how hot the star is. And then you have the information about how fast it's coming in. So that kind of tells you which stars types it's most likely to be coming from. And then you can go a step further and say, okay, now we've narrowed down some different kind of, basically we've narrowed down stellar type, some combination of stellar types and snow line regions in the disk that it could have come from. I think then once you compare it to, if you say, for example, that this thing was ejected by a giant planet, you go to what we know from exoplanetary science and we say, well, which stars are most likely to have a giant planet in the right region to eject a CO2-rich 3I Atlas? I think you might actually get somewhere in terms of figuring out what the most likely host stars are. But kind of stay tuned for that. Like my grad student, Tessa Frincke, who I think is on, you've talked to her before on the show. Yep. She's working on that right now. So we should have some results about that in the next couple of months.
I look forward to it. All right, Darryl, thanks for joining us again today. And I look forward to talking to you again as we continue to get a profile of 3I Atlas and future interstellar objects, because Vera Rubin is up and running.
Absolutely. Thanks, John. Thanks, Ross. Thanks for having me. Always a pleasure.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.